Okay, so moving on to the third process, which is a reversible constant volume process. So delta V becomes 0, and this constant volumes processes are also called isochoric processes. So since there is no change in volume, the change in work becomes equal to 0. So the PV work becomes 0. Okay. When this becomes 0, what will happen to the first law? So we know that dE is equal to del Q minus del W. This becomes 0. So this simply becomes dE equals dQ. Now, the fourth one, which is called the reversible adiabatic process, is a very interesting process. Okay? Now, adiabatic means del Q is equal to 0. Now, let's suppose you have a gas or you have a fluid, right? Now, if this gas, now if you have del Q is equal to 0, so let's first just write down the first law. Okay, this is del. What becomes? So this becomes 0. So this simplifies to this, right? Now, if a gas or a fluid, now if this fluid or gas expands, okay, let's assume that this gas expands. Expansion means del W is positive, right? So now when del W is positive, what do you think dE will become? Now dE will become negative, okay? For the opposite, now when dE becomes negative, what does that mean? That the internal energy of the system is reducing. So when a gas will expand, if this expands in an adiabatic way, if the gas expands, the internal energy will be lowered, and therefore it will cool down, right? Now, what happens when it compresses? Del W is less than 0, dE becomes greater than 0 because of the negative sign in here, and this, the gas will warm up. Okay, this is a very simple like first-hand understanding about what a reversible adiabatic process does. Okay, now these are the adiabatic processes. What are the adiabatic systems that you know? Anything that tries to keep the dQ as 0 is an adiabatic system, like an oven, right? You keep food in an oven, it tries to keep the heat. So that the dQ is trying to do that. So that becomes an adiabatic system, right? A refrigerator, it is trying to keep the heat out. It is trying to keep the temperatures to whatever that is. So the system is trying to be adiabatic, okay? Now, let's try and understand this by expanding on the first law, okay? Now, we have seen that the del Q becomes 0, so dE becomes negative of dW, okay? Now, what do you remember about dE? I remember that CV was dE by del T at constant volume. By this, dE became CV delta T, right? CV dt, dE. Now, this dW is basically PdV, right? This thing is P delta V. So work is PdV, the negative signs in here. Okay, so dE is equal to minus P dV, and dE is also equal to CV dt. So let's now equate these two equations. So this is equal to this, okay? Now, I write CV dt is equal to minus P times dV. Now again, there is this dt sign in here, and there is this P. So we want to remove this P and get in more terms like V. So we now have done this a few times. We know that PV is equal to nRT. So pressure is nRT by V. Okay? So we'll substitute the value of P in here. So let's do that. CV dt is equal to minus nRT by V times dV. Now we can bring this R and T over this side, right? So let's bring the temperature to this side. So this becomes this CV, this temperature comes this side, this becomes T, this remains nR by V dV, okay? Now what we'll do is we'll integrate this equation on both sides. So we will integrate this, and so this from temperature 1. So let's suppose the process went from V1 T1 to V2 T2. So we'll integrate from the initial to the final, initial volume to the final volume, okay? Now what this becomes is dt, so CV is a constant. Now let's assume that CV is independent of temperature, okay? So I assume CV is independent of temperature. Now if I assume this, CV comes out of the equation, and this becomes dt by T, and I integrate that, so this becomes ln CV ln T, okay? Now T is integrated from T2 to T1, okay? Simple. Now in here I have minus n, which is a constant, which I brought it out. R is a constant, I brought it out. I integrated ln from V to ln this, okay? All right, so we have this equation. Now let's do some magic in here, the magic of logarithms. If I get this negative sign inside, this becomes nR ln V1 by V2, okay? So let me write this equation in a colored chalk. This becomes CV ln T2 by T1 is equal to nR ln V1 by V2, okay? Now I'll call this equation 22. I think this equation was named 21, I failed to mention. So this was 21, this is 22. Now we will simplify this equation further, okay? I don't like this ln term, so I'll just remove those ln terms, okay? Remember that equation? Okay, so I'm just copying that equation one more time in here. So this is CV ln T2 by T1 is equal to n R ln V1 by V2. Remember, we took the negative sign inside, so the denominator and the numerator inside this logarithmic term have interchanged. Now, if we remove this ln sign, what it becomes is T2 by T1 to the power CV. And since both are natural logs, I can do this. And in here it becomes V1 by V2 nr. Now, I'll call this equation as 23. Okay, we'll simplify it further. I'll just get this CV to that side. Now I can do that by taking the, so if you have a square in here, so if you get the square root, this 2 appears to have gone to that side, right? So if I get the CVth root, so this becomes 1, and in here we get nr by CV, okay? And I'll call this equation 24. Now, these are the equations, these are the 3 equations which are the most important equations for dealing with adiabatic processes, okay? So these are the types of relationships that we'll be using to solve numericals and things like that in future. Now, why are adiabatic processes important? Like, why do we care about these things? Because most of the tropospheric, so we have an atmosphere on Earth, right? The lowermost, thickest layer is called the troposphere. Most of the tropospheric processes are adiabatic. And not just on Earth, on planets like Venus, Jupiter, Saturn, Titan, all these planets have a convective atmosphere. So, and they follow adiabatic rules in their atmosphere. So if we want to learn about these atmospheres, we have to have a clear-cut understanding about what an adiabatic process is, okay? Now, remembering this, let's simplify these equations even further. Now, you might remember from, I think, equation 19 was Cp minus Cv was nr, where n was the number of moles of the gas, okay? Now, if I divide both sides, this is Cp, if I divide both sides by Cv, I get this, right? Why did I divide both sides by Cv? Because I'm trying to get this number, nr by Cv. So you see how I am getting nr by Cv in here? So now, so if I write down something like this comes, okay? Now, Cp by Cv is called the adiabatic exponent, okay? So this term is termed as the adiabatic exponent, and shown by the symbol gamma, okay? This thing. Now, if we take this forward, so this thing becomes gamma minus 1 is nr by Cv, right? Okay, now if we, and this gamma is, as we have mentioned before, Cp by Cv. And if we have just 1 mole of a gas, we can represent that as this. Okay, but gamma is Cp by Cv. That's what is in here. Now, what we'll do is we will, let's call this equation 25. Okay. Okay. Now, let's substitute this value in here. Okay. Let's substitute the value of nr by Cv in here. So what are we getting here? So we get T2 by T1 V1 by V2. This was supposed to be nr by Cv, but now we have gamma minus 1. Okay? So we have T2 by T1 gamma T2 by T1 is equal to V1 by V2 to the power of gamma minus 1. Now, again, we shall be applying the ideal gas law. Now, a very simple form of the ideal gas law can be written as this, right? So we know that PV by T was a constant, right? So we can write P1 V1 by T1 is equal to P2 V2 by T2. Now, we have T2 by T1 in here. I want to replace that, okay? So what I'll do is, I'll take this T, like I'll rearrange this equation. So this becomes T2 by T1, P2 V2 by P1 V1, okay? So I'll just substitute that value, P2 V2 by P1 V1 becomes V1 V2 gamma minus 1. Now, what I'll do is I'll get these V1 to the other side and this V to the other side, okay? So this becomes P2 by P1 V1 times V1 gamma minus 1 and V2 times V2 gamma minus 1. Now, this has a power of 1, this has a power of 1. So when you have the same bases and you have a multiplication sign between them, you just add the powers. So this becomes P2 by P1 V1 to the power of gamma and V2 to the power of gamma. So I just wrote this, okay? So this can be rearranged again as this P2 V2 to the power gamma, and in here P1 V1 gamma. How does this look like? This looks like it's taking the form PV to the power gamma is a constant. And what is gamma? Cp by Cv. So this is equation 26. This is a very important equation describing any adiabatic process, and this equation is called the Poisson's equation. Okay? So let's take a few examples of like simplifications of this Poisson's equation. Now, equation 26 says PV gamma is a constant. Now, if we have a general equation in which we say, okay, let's suppose this is a number PVK, which is a constant, and we take different cases for this number, okay, different cases for this number, for this variable k. Now, if case 1, k becomes 0. Now, how will this whole equation will be simplified? So this whole equation will become P becomes constant. So this becomes an isobaric process, okay? So this becomes an isobaric process if k becomes 0. Now, if k is 1, this becomes PV constant. What is this process? This is an isothermal process. You can also remember Boyle's law, right? PV was constant. This was, and at that was the temperature was constant. For PV to be for P dot V to be a constant, it has to be an isothermal process, okay? And if K becomes equal to gamma, this becomes PV to the power gamma becomes a constant, and this becomes an adiabatic process. Okay? Now, this law, PV to the power constant gamma, is very typical of an adiabatic process, and this law will keep on coming again and again. So I would encourage you all to go through this whole process of finding out this PV to the power gamma, how constant, we go through once more and try and understand what were the assumptions that were involved in the derivation of this law, what are the different types of equations that came in while we were deriving this, what is the value of gamma, what is Cp, what is Cv. So this is a very important part in which you have to understand it very clearly in order to move ahead from this point.